Okay, ladies and gentlemen, welcome to the lectures on EC 393 Digital Signal Processing. In today's module, we shall learn about the fast Fourier transform. So, the fast Fourier transform. In short, this can be written as FFT. Now, broadly speaking, any form of Fourier transform operation is quite cumbersome. For instance, let us take any sequence x of n where 0 is less than n, which is less than n minus 1. In other words, n goes from 0 to capital N minus 1, which states that the length of the signal is equal to 4. Fair enough. Now let the signal x of n be equal to 1, 2, 3, 4, this being our original value, where n is equal to 4. Now then, according to the definition of DFT, we can write x of k to be equal to summation where n goes from 0 to 3, n goes from 0 to n minus 1 in our case being 3, x of n w n to the power of nk, rather w4 to the power of nk. So again we know w4 rather wn to the power of 1 is equal to e to the power minus j twice pi over n. Now what we are going to do is expand this summation and we get x of k to be equal to x of 0 times wn to the power 0, rather w4 to the power 0, x of 1 w4 to the power of k, x of 2 w4 to the power of twice k, and x of 3 w4 to the power of thrice k. Now once again solving for x of 0, we get x of 0 times w4 to the 0, w4 to the 0, w4 to the 0. Similarly, we will always get the value of x of 1, 2 and x of 3. Let us consider it to be so and so. So, it is needless to say that all of the terms, the individual terms of the quantities of x of k are complex in nature. So x of 0 is a complex quantity, might as well be a complex quantity. w4 to the 0 can also be any complex values. So if you look closely, the total number of complex multiplication required is one multiplication to multiply this term with this term. Similarly, there is one multiplication, 2, 3 and 4. So 4 multiplication for each row, 1, 2, 3, 4. So 4 multiplication for each rows and 4 multiplication along the columns. So the total number of complex multiplication will be 4 times 4. So here is 1, 2, 3, 4. There will be 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 different complex multiplications will be required in order to solve this sort of problem, which can be generalized and written. The total complex multiplication required is n times n, which is n squared, in solving DFT. And the total number of complex addition required is 1, 2, 3. 3 for computing each individual terms and similar 3 for each of the rows. So there are 3 along the columns and number of rows is 4. So total number of complex addition is 3 times 4, which is equal to 12. In general case, it is n minus 1 times n. This is n minus 1 times n. So these are the cases for complex multiplication and additions. Now, let us assume n we have assumed in our case to be 4. If n becomes 1024, what will be the case then? The total number of multiplications will be 1024 squared, and the total number of addition will be 1023 times 1024, which is obviously these two are very large number and undoubtedly is much more cumbersome for any computing device to calculate, which is concerned with limited memory value and processing speed. So that is the reason computing DFT is very much difficult for any computing device once the length of the signal gets larger, because there is obviously limitations in our memory space and processing speed. Now, in order to eradicate such difficulties, two celebrated mathematician, Professor J.W. Cooley along with J.W. Tukey, they are not brothers, although they have the same initials. Professor Cooley and Tukey came up with a paradigm shifting idea. Paradigm shifting in the sense, because of this invention, life on Earth, rather I should say, the life for electrical engineers became very much easier. They came up with an algorithm that revolutionized the calculation of DFT or any form of Fourier transform. This algorithm is known as the fast Fourier transform, otherwise known as FFT. And it is because of this FFT, signal processing has leapt forward by almost around 50 years. It is because of this FFT, it is quite possible for us to stream movie directly through the internet. and such high quality audio musics can be streamed over the internet. So the basic purpose of FFT is to simply solve DFT in a faster manner. So we can summarize FFT is nothing but a technique which is used to solve DFT in a quicker manner. Fair enough? Now let us see how does FFT works. So FFT work basically by an age-old Roman concept, that is a Roman technique of politics, which simply we can say is divide and conquer, used by famous Roman general Julius Caesar and Carthaginian general Hannibal. So what it does, it takes an endpoint DFT, divides it into n by 2 point DFT, which is further again divided to n by 4 point DFT, and so and so, until it comes to a point for which it is not further divisible. And what it does is solves that portion of the DFT and works its way up. So it divides the problem, conquers the smallest part, and works its way up the entire problem. So if in our case is 4, 8, 16, it will divide it to 2 and 2 point DFT. This will be divided into 4 point and 4 point DFT, and further divided into 2 and 2 point DFT. Similarly, you can understand it for 16 point, it will divide first into 2 8 points, then 4 points, and consequently 16 2 point DFTs. Further division in 2 point DFT is not possible. So this is how our FFT essentially works. So the only limitation of FFT is that n must be divisible by 2. Not necessarily, I must rephrase that, n must be divisible preferably by 2. Although divisibility with any other prime number is also acceptable, but what it does is it makes the calculation difficult and negates the purpose of using fast Fourier transform. So in our case, the division of n occurs as a radical power of 2. Say these are the number of divisions. And this is called the base or radix. Now radix can be 2, radix can be 3, radix can be 4, although making the radix 4 is very although making the radix 4 is very much irrelevant, because 4 can be divided into 2 point DFTs. So radix can be 2, 3, it can be 5, it can be 7. So any prime number we can take as radix. But it must be mentioned, the more we increase the number of radix, the value of the radix, the more difficult it becomes the solving of FFT. So the best possible way to solve an FFT is taking the radix 2, which is the most preferable case. Okay, now radix 2 FFT can be solved in two ways. Number one, it is called DIT FFT, which is decimation in time fast Fourier transform. So this is decimation in time fast Fourier transform, and another is DIF FFT, which is, as you have guessed, decimation in frequency fast Fourier transform. Let us not confuse ourselves with DIT and DIF. Remember, both DIT and DIF are alternative to our direct transform. Inverse FFT is completely different from these two operations. Many a times, students confuse between DIF and IFFT. This should not be the case and should be addressed immediately. So, without a further ado, let us solve a problem for radix 2 4-point DIT FFT. So, if our signal x of n is equal to 1, 1, 2, 2, this can be written as x of 0, x of 1, x of 2, and x of 3. First task in DIT FFT is to divide this signal into the even and odd components. So x even of n will take the even number of samples, which is x of 0 and x of 2, and make a pair. Similarly, we will take an odd number of sample, x of n, x of 1, x of 3. In case of our 8-point DFT, we take the even number of samples. There will be 4 even number samples and 4 odd number samples. So in case of our 4-point DFT, we got 2 even samples, 2 odd samples. So for 4, we get 2 even samples, 2 odd samples. For 8, first of all, we will get 4 even samples and 4 odd samples. These 4 even samples will have 2 even positions and 2 odd positions. So we will separate again the 2 even positions and the 2 odd positions. Similarly, these 4 odd samples will have 2 even positions and 2 odd positions, 2 even positions and 2 odd positions, which are separated. So you can see the concept of divide and conquer, how it works in DIT FFT. So we are implying that over here. So this sample will be equal to 1, 2, and this is equal to 1, 2. So in order to solve FFT, it is quite an interesting process. we draw two horizontal lines. Draw it in pairs. So these are two lines. These are our other two lines. This is our input side, and this will be our output side. That means we will supply the problem from this side and get the results over here. First, this line represents x of 0, which is equal to 1. Then, rather than x of 2, x of 1 I mean, we shall write x of 2. We will work with this pair. This will be x of 2, which is equal to 2. This will be x of 1, which equals 1. X of 3, which equals 2. So, we write the even pairs and the odd pairs together. Then what we do is draw some crisscrosses where the first and second line meets, the second and first line meets. The first line will meet with the second line, the second line will meet with the first line. Fair enough. Once again, we draw some crisscrosses over here. Now in this case, the crisscross will be a bit different. So in case of first line meeting the second line, we will meet the first line with the third line. So the first meets the third, second meets the fourth, third meets the first, second meets the fourth. Now here we will be given some multiplying factors, -1, -1, which is always similar or peculiar to our 4-point DIT FFT. Over here also we will give the multiplying factor -1 and -1 in the bottom two lines. Furthermore, here we shall be giving another two multiplying factor, W4 to the 0 and W4 to the 1, where W4 to the 0 is equals to 1, and W4 to the 1 is equal to -j. You can get the value from e to the power minus j 2 pi kn over n, and put the value of kn equals to 1 and n equals to 4 and expand using the Euler's equation, and you will get these results. Now let us solve our FFT. So the value over here is 1. So these points are our summation points in the right side. So 1 will go over here and 2 comes to this point over here. So this is 1 plus 2. Clear? Once again, now let us solve for this point. 1 goes down here and 2, this multiplied with -1 becomes -2. Point to be noted. So when a signal, when a value is traversing along a straight line, it needs to be observed first. So 1 is given over here, and when a value rises up to a summation point, it will be observed second. So this becomes 1 plus 2 rather than 2 plus 1, although the value will be same. Now in case a signal is going down a crisscross, it will be observed first, and if it goes a straight line, in this case it will be observed second. So 1 goes down the crisscross, it comes first, and negative 2 comes to a straight line, so it goes second. You can write minus 2 plus 1, it can also be written, but this helps in the calculation, as you can see in the future. So this value becomes 3 and this value becomes negative 1. So now 1 over here goes to this point, 2 rises up, goes over here, this becomes 3. So 1 goes down over here, this becomes 1, and 2 multiplied with negative 1 becomes minus 2, which is equal to minus 1. So this is our first stage. In the second stage, this value of 3, in between this point and this point there are no multiplying factors, so this value will carry over as 3. Same goes for this value, which will carry over here as 1. This value 3, when goes through this line, gets a multiplying factor of 1, so this becomes 3 times 1, which is 3. 1 going through this line gets a multiplying factor of minus j, so minus j times minus 1 is plus j. So we are able to determine all the values of this node. Now what we will do is solve for this right hand nodes. So 3 goes over here along the horizontal line, and 3 comes rising up, so 3 plus 3 is equal to 6. Negative 1 goes over here, and plus j rises up, so negative 1 plus j, the next value. 3 goes down, 3 multiplied by negative 1, so minus 3, which equals 0. Negative 1 goes down, j follows the horizontal path multiplied by 1, so it becomes minus j. And believe it or not, this is our required Fourier transform. So this is x of 0, x of 1, x of 2, x of 3, 9, I'm sorry, this is 6, minus 1 plus j, 0, minus 1 minus j. These are the value of the required Fourier transform. Another point to be observed: time domain signals in DIT in the left hand side will occur in pair of even and odd positions, but in the right hand side the frequency domain signal will occur consecutively. I hope the radix to 4-point DIT FFT is clear. Due to the constraint of time, I could not show you radix to 8-point DIT FFT, although I believe you can understand it quite well. So I should tell you to refer to the books and solve for radix to 8-point DIT FFT. So in this lecture, I will show all the radix to 4-point FFT, that is 4-point DIT FFT, DIF FFT, and 4-point IFFT. During practice, you shall practice for both 4 points and 8 points. You need not practice for 16 points because it becomes quite critical and it's not solvable in short time for our exam. So limit yourself to 4 point and 8 points. Practice for 4 points and 8 points FFTs. Okay, that being said, let us move on to the next problem, where we shall be solving radix to four-point DIF FFT. Say x of n is our given signal, which is 4, 2, 3, 2. Now, in case of DIF FFT, we need not divide the signals right away in the left hand side or the input side. So the 4 horizontal lines here, x of 0 is equal to 4, followed by not x of 2, rather x of 1, which is equal to 2, x of 2 is equal to 3, x of 3 is equal to 2. So in case of DIF FFT, the signal positions occurs consecutively. Once again, we draw our crisscrosses. So in case of DIF FFT, first we connected the first line and second line and the second line to the first line. Sorry. But in case of DIF FFT, we shall be connected in the first stage like this manner. So first line will be connected to the third line, second is connected to the fourth, third is connected to the first, and second is connected to the fourth is connected to the second. In the second stage, first is connected to the second, second is connected to the first, third is connected to the fourth, fourth is connected to the third. The multiplying factors, -1, -1. Here it will also be -1, -1. At this point, there are two multiplying factors, W40, which is equal to 1, W41, which is equal to -j. So as you can see, these two are quite similar. All we have done is taken the second stage and replaced it in the first stage of DIF FFT, and taking the first stage and replaced it to the second stage of our DIF FFT. So now let us start solving. 4 goes in this direction, 3 comes from here, this becomes 3, so 4 plus 3, it's 7. 2 goes here at this node, and this 2 comes up, becomes 2 plus 2 equals 4. 4 goes down at this point. 3 multiplied with this negative factor becomes -3. The result is 1. 2 comes down along this cross, and 2 multiplied with -1 becomes -2. The result is 0. These results are carried forward. 7 at this node, 4 at this node, since there are no multiplying factors. 1 when multiplied with 1 becomes 1. 0 multiplied with negative j will be 0. Once again we solve for this crisscrosses. So 7 goes along the horizontal line, becomes 7. 4 goes up, becomes plus 4. This becomes 7 plus 4 equals to 11. 7 goes down, becomes 7. 4 multiplied by negative of 1 minus 4, which gives us 3. Similarly, 1 goes plus 0. 1 goes down. 0 minus 1 is minus 0. This equals 1. This equals 0. So this is our required FFT, transformed signal, although there is a catch. The catch being that since we have not divided in this part, we must divide our signal over here. So this becomes x of 0, this becomes x of 2, this becomes x of 1, this becomes x of 3. So our required transform x of k is equal to 11, comma the first sample 1, comma the second 3, and 0. Fair enough. I think you have understood the 4-point DIT FFT and DIF FFT. Although I must emphasize that you must learn the 8-point DIT FFT and DIF FFT at your own expense, because there is a possibility question might come in the exam from the 8-point FFTs. Okay, in the final topic of today's lecture, we solve the radix to 4-point IDFT. So, if x of k is equal to 10 minus 2 plus j2 minus 2 comma minus 2 minus j2, then we are to solve the inverse discrete Fourier transform, and for that we require our horizontal lines. And these are our very beautiful horizontal lines. So in the right hand side, in the left hand side, this will be our frequency domain values, x of 0. No need to pair in the left hand side. This will be x of 1, x of 2, x of